Okay, so we've talked about a change of basis matrix, and what change of basis matrix does is it enables us to change the representation of one vector in one basis to a representation of that same vector in a different basis. Now we're going to go one step further. We know that linear maps can also be represented as matrices, and we can ask the question, how does the matrix representing a linear map change if we change the two bases that the matrix is based on? Remember that a matrix representation of a linear map requires a domain basis and a codomain basis. So what happens if we change the domain basis from B to B hat, and we change the codomain basis from D to D hat? How does that change the matrix that represents the linear transformation? Okay, so to summarize, we've talked about change of basis and its effect on vectors. Now we're talking about change of basis and its effect on maps. So this diagram is very illustrative. Notice the we have a vector space and we have two different bases, B and B hat. And we have the codomain vector space with two different bases, D and D hat. And we remember that the change of basis matrix is the representation of the identity with respect to these two different bases. Now, the change of basis matrix from D to D hat, similarly, is the representation matrix of the identity map here. We also know that the linear map H from V to W, when expressed in the bases B and D, gives us a matrix H. And similarly, we can say the same linear map H, if we use the bases B hat and D hat, will correspond to a matrix H hat. So the question now is, how is H related to H hat? Well, each one of these steps corresponds to a mapping. It also corresponds to a matrix multiplication. Notice also that the identity mapping here can go both ways. So if I want to get from here to here by matrix multiplication with respect to the bases B hat and D hat, I would simply multiply by H hat. But there's another way to get from here to here. I can go here, here, here. How do I go from here to here? Well, that's the identity. The inverse of the identity is also the identity. That's the identity. Here the domain basis is B hat. The codomain basis is B. Okay, so that takes me from here to here. To go from here to here, I'm applying the map H, and I'm using the bases B and D. So H is the representation of little h with respect to the bases B and D. And finally, to go from here to here, I'm using the identity map with respect to D and D hat. Okay, so here we have a identification of multiplication by H hat with a series of three multiplications, or a series of multiplication by three matrices. Okay. First, we have multiplication by rep B hat B of identity. That takes us from here to here. Now we're choosing B hat as our domain basis, B as our codomain basis. Then to go from here to here, we multiply by H. Then to go from here to here, we multiply by the representation of the identity with respect to domain basis B, D and codomain basis D hat. Okay, so we get this H hat matrix, which is the linear map H expressed with respect to codomain domain basis B hat, codomain basis D hat. And we can express that as the product of these three matrices. You're kind of going around the bend. Okay, let's do an example. We know the derivative map, and let's restrict to this three-dimensional space of second-degree polynomials. And let's consider these two bases. And let's represent this map with respect to B and D. We can also, well, let's continue with that. All right, if we look at these mappings here, the derivative map acting on 1 gives me 0. The derivative map acting on 1 plus x gives me 1, and you can show that 1 is equal to 1/2 times 1 plus x squared plus 1/2 times 1 minus x squared. Now, the derivative map applied to 1 plus x squared is going to be 1 plus 2x. Let's express 1 plus 2x in terms of the d basis. Now, there's a problem here because if I take 1/2 times the first basis vector here plus 1 times the second basis plus 1/2 times the third basis, if you do that, you're going to get 1/2 plus x squared plus x plus 1/2 minus x squared. That's 1 plus x, not 1 plus 2x. So there's actually a mistake here. This should be a 2 to get the derivative map. All right, let's look at the representation with respect to this second pair of bases of the same derivative map. The derivative of 1 is 0, and the representation of 0 with respect to these three basis vectors is 0, 0, 0. The derivative of x is 1, and you can verify that to represent 1 in this basis here, you have to take 1/2 times the first minus 1/2 times the second plus 1/2 times the third. You can do that power by power. For instance, here you'd have 1/2 times 1 plus 0 plus 1/2 times 1 gives me 1. 1/2 times x minus 1/2 times x gives me 0. And here I have minus 1/2 times x squared plus 1/2 times x squared gives me 0. So that does give me the x. Now remember, the derivative map acting on x, the derivative map acting on x squared should give me 2x. And unfortunately, this one doesn't work out. This is going to give me simply x. So to modify that, I think this should be a 1. And this one should be a 1. And if I do that, then this should be a minus 1. All right, let's check it. If I take 1 plus x, and then I add x plus x squared, that's going to give me 1 plus x plus 2, 1 plus 2x plus x squared. Then I have to subtract 1 plus x squared, that's going to give me 2x. So we have these slight modifications here. Okay, let's see if that works out with these corrections. All right, to do the conversion, we need to find the change of bases matrices. So to get this one, if I start with beta hat and go to beta, start with b hat and go to b of the identity. Now 1 expressed in the b basis is 1, 0, 0. X expressed in the b basis is going to be, it looks like it's going to be minus 1, 1, 0, which is correct. And x squared expressed in the b basis is going to be 0 minus 1, 1, which is correct. So that's correct matrix representation of the identity from beta hat to b. Now we want the matrix representation from d to d hat. Now 1 plus x squared expressed in the d hat basis is 0, 0, 1. So that's correct. X expressed in the d hat basis looks like it's going to be 1, 1 minus 2. I'm sorry, no, it's 1/2, 1/2 minus 1/2, which is correct. And let's just make sure about this. 1 minus x squared expressed in this basis is going to be 1 minus 1, 0. So this one works out correctly. Now, in order to get the representation with respect to beta b hat d hat of d dx, we can find that directly here, but that should also be equal to this representation matrix times this matrix here, so I need to change that to a 2, times this matrix here. If you work out this matrix multiplication, you can verify that that will give you this matrix here. Okay, so you can work that example through yourself. All right, now what we've shown here is that this matrix here, the representation of BD with respect to BD of this mapping, and the representation with respect to B hat D hat of this mapping, certainly these two matrices are related in some way, in a very deep way, that they both represent the same linear mapping. And we can relate them algebraically by taking this matrix here, multiplying on the left and right by invertible matrices, and obtain this one. So we're going to generalize that definition. We're going to say, suppose you can take one matrix and multiply on the left and right by invertible matrices to get another matrix. Then those two matrices are equivalent in some sense. And in fact, those two matrices do represent the same linear map with different pairs of bases. Okay? So that motivates this definition. If we have two matrices that are the same size, they don't have to be square. Okay? As long as they're the same size. We say they're matrix equivalent if there are non-singular matrices P and Q such that H hat is obtained from H by multiplying on the left by P and on the right by Q. Now, matrix equivalence matrices represent the same map with respect to appropriate pairs of bases. Why is that? Because any non-singular matrix represents a change of basis, and any non-singular matrix here represents a change of basis. So we can simply write down those change of bases and get a expression of this with respect to a different basis. We can in fact check that this is an equivalence relation. Remember, there are three conditions for an equivalence relation. One is reflexive. A matrix has to be matrix equivalent to itself. Symmetric. If H hat is equivalent to matrix equivalent to H, then H is also matrix equivalent to H hat. And transitive, if H is equivalent to H hat, which is equivalent to H double prime, then H is equivalent to H double prime. So remember those three conditions of equivalence relation: reflexive, symmetric, and transitive. Once you've established those conditions, that means that all matrices. Now here, notice that these H and H hat are not necessarily non-singular. So we establish this equivalence relation on all matrices, not necessarily non-singular matrices. But since we have an equivalence relation, the set of equivalent matrices will form an equivalence class. In other words, all matrices that are equivalent to H will form a class, and we can partition, that is divide, the set of all matrices into these equivalence classes. Now remember, when we did this before, we tried to find one representative in each class that basically tells us what that class is all about. It characterizes that class. And that's what we're going to do now. Any m by n matrix of rank k is matrix equivalent to the m by n matrix that's all zeros except the first k diagonal entries are ones. Okay, so we can use this equivalence operation, multiply a matrix on the left by a non-singular matrix and on the right by a non-singular matrix. Now remember, a non-singular matrix must be square, so this P is square and this Q is square, although the H is not square. Let me just briefly show how that works. If H has this size, if H is m by n, then that means that P would have to be m by n, m by m, and Q would have to be n by n. Okay, so P and Q are not necessarily the same size, but the dimensions of P and Q must be compatible with the dimensions of H. Okay, now where was I? All right, so any matrix, whether square or not, can be expressed in this form. It has ones down the diagonal to a certain extent. Now notice if there are zeros on the diagonal, this matrix is certainly not non-singular. But as I said, we're characterizing all matrices, not just non-singular matrices. Notice that we can divide this matrix up into pieces. And here we have an identity matrix in the top left-hand corner. In the bottom left-hand corner, we have a square matrix of zeros. And on the sides, we have rectangular matrices of zeros. So in this format, these z's are not necessarily the same size. This matrix will always be square. Is that really true? No, that's not true. I'm sorry, I shouldn't say that. That matrix is not necessarily square. So none of these matrices need be square. Okay. All right, now, any m by n matrix of rank k is matrix equivalent to the m by n matrix of all zeros except the first k diagonal entries are ones. How do you do this? Basically, what you do is you row reduce to row echelon form. If you row reduce to row echelon form, you're going to get your last rows to be zeros, and then you're going to have the row echelon form where you have ones in certain columns, and those are the leading entries. And then you'll have other columns that may have non-zero entries in them. Okay, but then you can column reduce. When you column reduce, you can eliminate those columns that have non-zero entries because you add multiples of the columns that have just ones in them. Those columns that have non-zero entries correspond to free variables, and these correspond to non-free variables. But these columns can be used to reduce those other non-zero columns to zero. Okay, so that's the idea. You row reduce to get rid of excess rows, and then you column reduce to get rid of excess columns. Okay. All right, matrix equivalent is characterized by rank. Notice that the rank of this matrix will simply be the number of non-zero rows. So any two matrices that have the same rank will have the same number of non-zero rows in this final form. So they will be matrix equivalent. So matrix equivalence classes are characterized by rank if the matrices are the same size. Okay, so for instance, these two matrices are not matrix equivalent because you can show they have different ranks. And these two matrices, as long as you can show they're the same rank, they are matrix equivalent. And you could do that explicitly by row reducing this and then column reducing. Okay, and that's it.